Hi, hello everyone. This is your educator, your tutor, your friend Sanjay Vishwakarma. I welcome you all to yet another session of We Learning. We Learning is a platform which focuses on providing right to quality education for all. Do watch this session. If you like it, do press the like button. Share it with your other friends who are preparing for their boards and competition as well. Alright, subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Now, without any delay, let's get started with today's session. We were doing electrostatic potential and capacitance, and this is lecture number 12, where we'll be seeing combination of capacitance, part 2. Last time we had seen combination of capacitance part 1, where we saw series, parallel, and the mix of series and parallel, right? Along with that, we did some questions based on that. Here we'll be seeing more type of combinations, okay? Anyways, all the combinations, finally they will come to, the resultant will be either series or parallel, or the mix of series and parallel, right? But initially when you look at those combinations, you won't make out whether it is series or parallel. We'll learn how to make it, how to convert it into that particular combination, okay, where you can understand. First, potential method type questions, okay. Find the equivalent capacitance between A and B. So here you are given with a circuit. A and B, let's say across A and B, a battery is connected, fine. You have to find equivalent capacitance of this particular circuit between A and B, fine. Now, let's say, or if I connect a battery, if the EMF of the battery is V, this will be V, this will be 0, right? Then only the potential difference will be V. Now, that means A is at a potential V, higher potential, right? It is at a lower potential 0. Now, if A is at V, understand, from here can you tell whether it is series or parallel? No, right? If you don't know this way of how we are doing it, it will be difficult to make out whether it is series or parallel. Let's understand. It is a very easy question, by the way. Now, if this is V, see, from here to here, if you move, nothing is there. So the potential drop will not happen. No capacitor, no resistor, nothing is there. So here also it will be V at this connection. From here to here, when we are moving, there is no capacitor or resistance in the middle, right? No potential drop will happen. That means here also the potential will be V. Here it is V, I am moving. The potential is same. Here also it will be same. Now when we come from here to here, a capacitor is there, potential drop will happen. From here to here, a capacitor is there, potential drop will happen. So till here, I hope you understood. This is at V, this is at V, this is at V. From here, let's see, this is at 0. That means from here to here, this will also be at 0. From here to here, once we come, this point, this will also be at 0. Correct? This is at V, this is at 0, this is at V, this is at 0. Now, if I make an equivalent circuit for this, see, we have one point A, alright, where the potential is V. We have another point B where the potential is 0. Correct? Now between V and 0, one capacitor is this. Between V and 0, one more capacitor is this, and this capacitor is also between V and 0. That means potential drop across each capacitor is V. One side V, another side 0. What is the potential drop across this capacitor? V minus 0. What is the potential drop across this capacitor? V minus 0. What is the potential drop across this capacitor? V minus 0. Across each and every capacitor, potential drop is same. That means all the three capacitors are connected between A and B. Correct? See, this capacitor between V and 0, 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 this capacitor between V and 0. Clear? Now can you see what is this? It's a parallel combination. Parallel combination means C equivalent is equal to C plus C plus C, that is equal to 3C. Clear? Easy? I hope now you can do this type of questions. Okay. Let's go to the next one. This circuit is there. Now how will we do it? Let's say instead of V and 0, we will only write A and B, okay? So this is A, that means this point is at A. This point A, this point is also at A. Correct? Now then a potential drop will happen because the capacitor came in the middle. This B, this is B, that means this is also B. This point is also at B. That's all what we know. So now there are total 2 points, A and B. Capacitor between A and B. So if you see this capacitor is between A and B, and these 3 capacitors are between A and B. That means between A and B, one capacitor, this will come. And between A and B, these 3 capacitors are also coming. Now can you tell what is this? These 3 are in series, this is in, and this, they are in parallel, right? So this will be C, 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 this is C. So now C equivalent will be, for this 3 if we solve, these 3 are in, let's say C equivalent 1. Or let's take C1. This, all the 3 resultant I am taking as C1. So 1 by C1 will be equal to 1 by C plus 1 by C plus 1 by C, that is equal to 3 by C. So C1 is equal to C by 3, right? Here the resultant of all the 3 is C by 3. This is C by 3. So this is basically C by 3, correct? A and B. So C equivalent is equal to C plus C by 3. That is equal to 3C 4C by 3. Correct? This is the answer. C by 3. C by 3 plus C, 4C by 3. Clear? I hope now you can do it. Let's see the next one. A bit tough, right? It's not tough. If you know the concept, it becomes easy. See here. This is A. If this is A, this is A. This is also A. B, and then there will be a potential drop. So now this one more wire is there. This cannot be A, neither it can be B. Let's take it some point as C, or C is already there. Let's take some point as let's say X. Okay. This point is also X. See, if I consider this as X, this point is also at X, and this point is also at X. Correct? Now there are total 3 points, A, X and B. Let us make those points A, X and B. Fine. This capacitor is between A and X, right? This capacitor is also between A and X, correct? This capacitor is also between A and X. Correct? Now these 2 capacitors are between X and X. How is this possible? Between X and X, between one point only 2 capacitors. Either there should be 2 points, then only the term between can come, right? X and X, this is invalid. This doesn't exist. And that too, you have heard about current. Current goes on the path with lowest resistance. So if it has to go from here to here, it will choose this path. Why will it choose here, right? This wire we can remove because they both are in same potential. If they both are in same potential, that means there is no potential drop across these. The charge is not flowing in this. We can remove this, right? So from between X and B, this capacitor is there, right? So between X and B, this is the final circuit. Now it became easy. So first when you look at it, it is complicated. But from this potential method, this becomes easy. Now see, these 3 are in parallel. This is in series. So here, if these 3 are in parallel, so this is like 3C, C. Oh. Or I'll make on the next page. Between A and B we had to find out. Fine. So this will be 1 upon C equivalent is equal to 1 by 3C plus 1 by C. Solving it easily, 3 by 3C. So that is equal to 4 by 3C. So C equivalent is equal to 3C by 4. Clear? C plus 3C, 4 by 3C by 4. Note it down. Next, Wheatstone bridge type combination. So I hope you understood potential type. Now second is Wheatstone bridge type combination. What is Wheatstone bridge? You will study this in detail in your electricity chapter. Fine. Here also I'll explain you. Not a problem. See here, this kind of combination if you see, can you make out whether it is series or parallel? No, right? This, then this comes in middle, then this, then again this wire comes in middle, then this. How to do this? Here, whenever you see this kind of combination, the first thing what you have to see is if the ratio of the capacitance of these two is equal to the ratio of the capacitance of these two, then we can remove this wire from the middle. I'll write it, okay? If C1 by C3 is equal to C2 by C4, if this condition is there, this condition is known as balanced condition. We will say Wheatstone bridge is balanced. Fine? This is balanced condition. If this is there, then X and Y, let's say this point is X, this point is Y. Here this is A, this is B. What is this? There will be a potential drop. We don't know how much. Here also there will be a potential drop. We don't know how much. I consider this point as X, this point as Y. X and Y will be at same potential. Or let's say are at same potential. Because they are, that's why it is balanced. X and Y are at same potential. And just now what we saw, if 2 points are at same potential, the connection which is there in between them, we can remove this. There is no potential drop. Here, these 2 points are at same potential. So the current will not flow here. This capacitance is just like that, invalid. Okay? Here this wire, you can remove it. So if you remove that wire, the final connection will be like this. There is no need to remove this wire. If it is there also, current is not flowing there. Resultant circuit will be like this. Clear? So if this is there, now can you find out equivalent capacitance? Yes. These two are in series. These two are in series. Then this one and this entire one are in parallel. Fine. Now let's see the proof. How the current is not going here, or why this we have removed. Okay. Tell me one thing first. If C1 by C3 is equal to C2 by C4, if this is there, X and Y are at same potential, this we can say. Now can we say the opposite of this, that if X and Y are at same potential, C1 by C3 will be equal to C2 by C4? Yes, definitely. If this is true, then that is true. Fine. If this is true, then this will be true. So we'll consider this one. Alright, and we'll try to prove this. So now, proof. First, what we are taking is, if this is the circuit, if this is X, this is Y, what we are considering? Let X and Y be at same potential. Fine. Same potential means, obviously current is not flowing in this. We have already assumed. Now assuming this, if this relation comes, then that means our assumption was correct. This, if that is true, this is true. Clear? All right. Now, see here, this is connected to battery. At this point, let's say VA is there, or let's say V is there. Fine. If V voltage is there, this is V, this is 0. So from here, this will be V. From here this will be at 0. Fine. So now V minus X, here the potential is X, here the potential is Y. V minus X will be equal to potential drop at C1. Let's say Q amount of charge is going here. Now here the charge will distribute as Q1 and Q2. Are yes or no? The way current distributes, the same way charge will distribute. Fine. That means in this entire arm Q1 is flowing, in this entire arm Q2 is flowing. We have already considered that the charge is not flowing in this. Fine. Here also Q1 is going, here also Q2 is going. Fine. Potential drop across P1 can I write as Q1 by C1? Correct? Q is equal to CV. So V is equal to Q1 by C1. Potential drop. This is the first equation. Then potential drop across this C3 can I write as V minus Y is equal to Q2 by C3. Correct. Now one more thing. This Y is nothing but X only. This Y is nothing but X only, right? So I can remove this Y and write as X. All right. Both are at same potential. The value of potential is same. Now from here, X minus 0 is equal to Q1 by C2. Third equation. That means X is equal to Q1 by C2. From here, Y minus 0 is equal to Q2 by C4. That is the fourth equation. Correct? Now this Y I have written is X is equal to Y. Since. Fine. Here also, this Y is there. This Y I can replace by X. Since Y is equal to X. Alright. So we have got this 4. We have got the value of X as Q1 by C2. And the value of X is Q2 by C4 also. That means Q1 by C2 is equal to Q2 by C4. Array, these two are equal. Both are the value of X. So from here, if I see from 3 and 4, I can write from 3 and 4. Q1 by C2 is equal to Q2 by C4. From here I can write Q1 by Q2 is equal to Q1 by Q2 is equal to C2 by C4. Remember this. Fine. Now, from 1 and 2 what can we get? From 1 and 2 we are getting that Q1 by C1 is equal to Q2 by C3. Right? From 1 and 2, Q1 by C1 is equal to Q2 by C3. Correct? See? V minus X is this, V minus X is this. So these two are equal. Now, from here I am getting that Q1 by Q2 is equal to C1 by C3. Q1 by Q2 is equal to C1 by C3. Let's say this is equation number 5, this is equation number 6. Now from 5 and 6, Q1 by Q2 is C2 by C4. Q1 by Q2 is also C1 by C3. So can I write C1 by C3 is equal to C2 by C4? Hence, proved. That's what we wanted. Correct? C1 by C3 is equal to C2 by C4. So we have considered that X and Y are at same potential. The charge is not flowing through this. Considering this, we got this. That means if this is true, this will be true. Alright, got it? Okay, let's see a question. Find the equivalent capacitance in the following circuits. This is the circuit. You have to find the equivalent capacitance. Now, if you don't know the Wheatstone bridge, you will not be able to solve it. It will be very difficult, complicated. So how to do? We know Wheatstone bridge. The very moment we get this question, the first thing what we will see is the ratio of this and the ratio of this and this. Fine. Let's find out. 2 microfarad. Here the ratio will be 2 microfarad divided by 6 microfarad. How much is it? Or let me write here. There I can solve. 2 microfarad divided by 6 microfarad. That is equal to 1 by 3. Here 8 microfarad divided by 24 microfarad. That is again equal to 1 by 3. Are yes or no? So this, the ratio of 2 is to 6 is equal to 8 is to 24. So since they both are same, I can remove this particular wire. Right? The charge is not going in this. These two are connected in series, these two are connected in series. And this arm and this arm are parallel. Fine. So now from here, the circuit what I got is A, B. This is 2, this is 8, this is 6, this is 24. Now can you solve it? Obviously, these two are in series. Let's say this is C1. 1 by C1 is equal to 1 by 2 mu plus 1 by 8 mu. That is equal to 8 plus 2, 10 upon 16. C1 will be equal to 1.6 microfarad. If you do the calculation, you will get this. Correct? This will be 10 by 16. Reversing is 16 by 10, 1.6 microfarad. C2, 1 upon C2 is equal to 1 upon 6 microfarad plus 1 upon 24 microfarad. What will be the answer? C2 will be equal to 24 plus 6, 30, divide by 144, 30 by 144, reciprocal, 144 by 30, 144 by 30. 3 tens are, 3 fours are, 3 8s are, 4.8 microfarad total. So now the connection is like this. A, B. This is 1.6. This is 4.8. So finally what we'll get? C equivalent is equal to 1.6 plus 4.8. That is equal to 4.8, 5.8, 6.4. 6.4 microfarad. Clear? Easy? Note it down. Next, ladder problem. So now third kind of question. It's getting interesting slowly. Let's see. Find the equivalent capacitance in the following circuit. So this is the circuit. We have to find equivalent capacitance between A and B. Alright. Now this is going till infinite. If you see this is C, then C, then C, then C, then C, then C. Like this goes till infinite. It's infinitely long circuit. How will you do this? We don't know the number of capacitance. We don't know the number of capacitors only. How will we do this? See here. Whenever you get this kind of question, infinite, there will be some kind of series which will be forming. Okay. We need to see that. Some kind of symmetry will be there. We need to see that. Now see the symmetry here. This and this. In here, here. If you see this again, here. Again if you see, here. Like this, another capacitor will be here and another will be here. Like this, another will be here, another will be here. Now we know this particular unit is repeating. Correct? This is first unit, second unit, third unit, fourth unit, fifth unit, infinite unit. This unit is repeating again and again. Now see one more thing. If I cut this from here, okay, from here, if I make another circuit, or if I remove this part, I'm removing this part. From here, if you see, is this and this entire looking the same? Okay, let me make you understand. I have cut this portion out. I have thrown it away. Fine. I am only having this much. Let's say. If I make this much, it will be right. This unit. And the same we know it is repeating like this. and it goes till infinity. See this circuit and see this entire circuit are both the same. That means the equivalent capacitance of this circuit and the equivalent capacitance of this entire circuit is same. In quadratic equation, you might have done these kind of questions in mathematics, right? Where x under root x something like this comes, correct? A symmetry kind of thing comes. Here also if you see, so now if I consider this as A and B, the equivalent capacitance of this, that means this from here, I can remove this entire thing. Now suppose equivalent capacitance of this entire circuit is C equivalent, fine, or let's say equivalent capacitance of this entire circuit is X. C equivalent is equal to X for this entire circuit, fine. This I have cut and I have made it here. For this entire circuit, let's say C equivalent is equal to X. Now this and this entire circuit, if I remove this, are same only, because this is also going till infinity, this is also going till infinity, fine. That means the C equivalent for this is also X. If C, or you can say if C equivalent for this we have to find out, we have considered this as X. For this circuit also C equivalent will be X only, fine. So this particular part I can remove and I can make a capacitance as C equivalent here. Here, what I have done, I have removed that part and replaced it with C equivalent, because the equivalent capacitance of this entire circuit is this X. This is X now, fine. This is C, this is C. Now, again here, these two are in parallel. So now what I can do is, this is A, this is B. This is C plus X. Now C and C plus X are in series. If C and C plus X are in series, so I can write 1 upon C equivalent is equal to 1 upon C plus 1 upon C plus X. What is C equivalent? X only. C equivalent is what? X only. Correct. So now from here, if you see, if you try to solve, 1 by X is equal to 1 by C, or let me just open this completely. C plus X plus C divided by C square plus Cx. From here, if I cross multiply, C square plus Cx is equal to Cx, 2Cx actually. This is C plus C, 2C. 2Cx plus X square. Correct. Now from here, X square, this Cx, if it goes here, it will be plus Cx. 2Cx minus Cx is Cx. And this will be minus C square is equal to 0. It's a quadratic equation. Solve this quadratic equation for X, you will get the equivalent capacitance. Clear? Let's do it. Now from here, okay, X is equal to minus C plus minus under root B square minus 4AC, right? C square plus 4C square divided by 2. I hope you remember this formula. X is equal to minus B plus minus under root B square minus 4AC upon 2A. That is the same what I have applied. Fine. That is minus C plus minus. Now here, 5C square. C square will come out as C. So C root 5. C plus minus C root 5 divided by 2. Capacitance cannot be negative. If I remove the negative one, I mean here. So this will be minus C plus C root 5 divided by 2. So C common, root 5 minus 1 by 2. Correct? If you solve this, what do you get? C common, root 5 minus 1 by 2. Or we can say root 5 minus 1 by 2 times of C. Root 5 minus 1 by 2 times of C. This is what? X is C equivalent. Clear? I hope I have done correctly. This looks like C square. This is a different thing. Fine. 5 root 5 c minus c common root 5 minus 1. Correct. Now this question you have to try doing on your own. Try more ladder kind of problems. Fine. I hope you understood this. Easy it was. All right. Next, symmetric circuit. So now what are symmetric circuit? Again, very complicated. You will see when you will see it, it will be like very complicated, but they are very easy. Find the equivalent capacitance in the following. These all questions you won't get in boards for sure. Okay. See this particular circuit. Can you make out whether it is series or parallel? This, then suddenly one wire comes, then suddenly one more wire comes. Here also one more, then here one more, then here it joins and one more capacitance. How will we do this? See, whenever you see a very complicated circuit, try to find a line of symmetry if it is there. Okay. See here, can you find a line of symmetry? Can you find a line of symmetry? See this line. If I fold it like this, can I fold? Or if I keep a mirror here, this part is entirely the reflection of this part. Or if I keep a mirror here, this part is entirely the reflection of this part. I can make a line of symmetry like this. Yes, see. This one plate is this side, one plate is this side. Either half plate is this side, this side. This plate, this plate, this plate, this plate. This is completely symmetric about this line. So whenever you see any circuit which is completely symmetric about a line, on that particular line of symmetry, if there is any capacitance, if there is any wire, remove that. Fine. To solve it, I am telling you a trick. In this line of symmetry, this capacitance is coming. Remove this. All right. On removing this, the circuit what will become is like that. Remove the capacitance along the line of symmetry. Fine. Don't remove this one. This is not along. Along the line means overlapping with the line. See, this wire is overlapping with this line, but this wire is like this. Correct? That's what I have written. The circuit will become like this. Now, can you solve this? Yes. These two are in series, these two are in series, and then this is there. All these three arms are in parallel. So I can make it as, this will be C by 2. This will again be C by 2. Now I'm expecting that you can do fast without solving so much. There is no need of writing 1 by C, 1 by C. If two equal capacitances are connected in series, the resultant will be C by 2. If 3 equal capacitances are connected in series, the resultant will be C by 3. If n equivalent capacitances are connected in series, suppose 2 equal capacitance are connected in series, the resultant will be C by 2. 3 equal capacitance are connected in series, resultant will be C by 3. N equal capacitances are connected in series, resultant will be C by N. So that's what I have written, C by 2, C by 2, C. So now this is point A, this is point B. Fine. Parallel, C by 2 plus C by 2 is C, plus C, 2C. Resultant will be this is A, this is B, this is C by 2, this is C by 2, this is C by 2. Sorry, this is C. So from here, C equivalent is equal to C by 2 plus C by 2 plus C, that is equal to 2C. Clear? Easy question? Okay, now do one more for symmetry. How? See here, you can find two lines of symmetry. One vertical, one horizontal, right? This and this both. Do not consider this line of symmetry. because you have to find for A and B. Fine. You can consider and remove these two also. But if you see this, try to remove that line which is not along AB. Fine. All right. So now if I remove this line of symmetry, my circuit will be like this. This line of symmetry is there. Capacitance along this line of symmetry I have removed. So what I got? I got this. Clear? See, if you remove this also, the question will not become easy. Because again then this will come. Let's say if you remove this line. Okay. Our motive is to make the question easy for us, not difficult for us. This will be like this, then this, then this. You have removed this. Okay. Then this, then this. Did it become easy? No, right? Because again this line is there, which is disturbing, and it is not a Wheatstone also. I guess it is a Wheatstone. You can solve this. Fine, but not every time it will be. Okay. So our motive is to make the question easy. So here if you see, this line is removed. Now see, these two are in series, these two are in series, these two are in series, and all the three arms are in parallel. You can easily do this. Fine. It will be, okay, A, B. It will be C by 2, C by 2, C by 2. Correct? So this will be C equivalent is equal to 3C by 2. Fine. Note down. Now let's do this one. Parallel plate type combinations. Again, very interesting. Find the equivalent capacitance between A and B if capacitance between any two plate is C. So now we are given with this. Again, it doesn't look series or parallel, right? See these plates. If this side is having positive charge, let's say, then this plate just in front of it will get a negative charge. Correct? Negative charge is on this side of the plate, so the other side of the same plate will have positive charge. Because of this positive, this plate, this side negative charge will come. Because this side is negative, other side will be positive of the same plate. Now see what is happening. This is one capacitor. Correct? This is another capacitor. This is another capacitor. Like this, there are capacitors. But how many capacitors will be there if n plates are there? Again, see it closely. When two plates are there, one capacitor is there. Right? When three plates are there, let's say these three plates, 1, 2, 3. So how many capacitors are there? One this capacitor and one this capacitor. When three plates are there, two capacitors are there. Correct? When four plates are there, see. When I am considering four plates, three capacitors are there. 1, 2, 3. That means if n plates are there, n minus 1 capacitors will be there. Correct? So here total capacitors are n minus 1 connected in series. This is basically n minus 1 capacitors connected in series. Clear? So now you can do it. N minus 1 capacitors connected in series means equivalent capacitance will be C upon n minus 1. Just now we discussed something like this, right? Here this is A, this is 1 capacitor, 2 capacitor, 3 capacitor, like this. This is B, n capacitors connected. Fine. N capacitors connected in series means 1 upon C equivalent is equal to 1 upon C plus 1 upon C plus like this n minus 1 upon C. Not n minus 1. 1 upon C n minus 1 times. This is n minus 1. These are n minus 1 capacitors connected in series, fine. So this is 1 by C n minus 1 times. That means this is 1 upon C equivalent is equal to n minus 1 by C. C equivalent is equal to C upon n minus 1. There was no need to write so much. It was easily understandable. If n minus 1 capacitors are connected in series, all the capacitance is C. So the equivalent capacitance will be C upon n minus 1. Clear? Next. Something more interesting. Okay, let me just write it here. I'm writing directly, okay? C equivalent is equal to C upon n minus 1. Fine. Next. Find the equivalent capacitance between A and B, and now this is the combination. Something like a snake. Fine. How will we do this? Again, very easy. Potential type question. This is potential A, this is potential B, let's say. Okay? If this is A, then this plate is at potential A. This plate will be at potential A. If this is B, this plate will be at potential B, and this plate will also be at potential B. So now this plate is at A, this plate is at B, this plate is at A, this plate is at B. There are 2 points A and B. Correct? Between A and B, this capacitor is there between A and B. This capacitor is there between A and B. Again, this capacitor is there between A and B. See, this is at A, this is at B. So this capacitor is also between A and B. If you see this capacitor, again this plate is at A, this plate is at B. This capacitor is also between A and B. So what is this? It's a parallel combination of 3 capacitors. So C equivalent, okay, C equivalent is equal to C1 plus C2 plus C3. Fine. This is C1, this is C2, this is C3. We don't know if the capacitances are equal or not because it is not mentioned. In the last question, it was mentioned between 2 plates the capacitance is C. Here it's not mentioned, so it can be different also. Fine. Next. Find the equivalent capacitance between A and B. This time, this is the connection. Try solving it on your own. I'm doing it here. You try on your own. If the answer is same, pat yourselves. Fine. So now if this is A, this is also A. This plate is also at A. This is B, this plate is at B, and this plate is also at B. Now there are 2 points A and B. This capacitor, between A and B, one capacitance is this. These 2 plates are between B and B. Not possible, right? So this is no capacitance. This capacitor is not there. This is only one plate we can consider. Fine. So now again these 2, if you see between A and B, again one more capacitance is there. You just have to find capacitance between 2 different points. That's all. A, B, one capacitor. A, B, one capacitor. B, B, we cannot consider as a capacitor. Fine. So this is C1, this is C2. Again, C equivalent is equal to C1 plus C2. Clear? Next. Now, see this one. Here, area A is given and the distance between 2 plates D is given. So can we write capacitance between 2 plates as epsilon naught A by D? Or yes or no? The area of each plate is given as A. Distance between any 2 plates C, it is D. So the capacitance between these 2 plates, epsilon naught A by D, right? So we got this as C. Here we have to answer in terms of A and D only. Okay, because these are given. For making our question easy, we have just wrote C is equal to epsilon naught A. Now this plate is at potential A. This plate is at potential B. That's all. Rest are new different points. This plate, let's say, is at capacitance C, so this and this are connected. This is also at capacitance C. Fine. This plate is, let's say, at capacitance D, at potential D. Sorry, this is potential C. This is at potential D. So now there are how many points? 4 points. A, B is somewhere at the end, C, D, B. Fine. Now see here. This capacitance is between C and D. So I'll make one capacitance here. This capacitance is between A and D. See, A, D. A and D means this will be something like this. This capacitance is between A and C. Fine. This capacitance is between B and C. So C is here, like this. So this circuit, if I shift it like this, can you understand how is this? These two are in series, see? Right? Then this and these two are in series. If I club it, it will be one. They both are in parallel. And then this entire thing and this is in series. If I make this only properly, it will be something like this. Okay. Let me get a fresh page. I don't think I'll get. Okay, here only I'll make properly. Now see here. If I just modify the circuit properly, it will be something like this, correct? That's what we had made. This is C point. This is B point. So A and D, one capacitor is there. D and C, one capacitor is there. C and B, one capacitor is there. A and C, one capacitor is there. The same circuit, I have just modified it properly. I have just turned it a bit. Fine, this side. Now see, these two are in series. All are having capacitance epsilon naught A by D, correct? Area A, D. Area A, distance D. Area A, distance D. Area A, distance D. Fine. So this is C, this is C, this is C, this is C. Fine. So this both will club together and become C by 2. I'll make it here. So here if I make it C by 2, this is something like this. This is C by 2 and C parallel, we'll add it up. 3C by 2, 3C by 2 plus C, 5C by 2, correct? Sorry, this will be 1 upon C equivalent is equal to 2 by 3C plus 1 by C. So this will be 3 by 3 if I do, 5 by 3C, 3C by 5, correct? So here C equivalent will be 3C by 5. But the answer will be 3 epsilon naught A by 5 here D. This is our C equivalent. Correct? C is epsilon naught A by D. We have to replace that. 3 epsilon naught A by 5D. I hope it's right. Again, I'll just check. 2 by 3C plus 1 by C, 3 by 3C, 5 by 3C, 3C by 5. Correct. I hope you got it. Again, try it on your own. All right. So I hope you enjoyed today's session. You enjoyed practicing the equivalent capacitance. Try more kind of combinations. Again, they are very interesting. All right. In the next session, we'll be seeing effect of dielectric on capacitance. Okay. Before that, whenever you see any kind of circuit like this, any combination, First, see whether it is series or parallel. If you are not able to see, if you are not able to find out, then see which one can you apply in this. Fine. Whether it's a Wheatstone, or can I do it with potential method, or is it a ladder, or is it a symmetry forming? You have to identify which kind of question is this. Maybe in the same question, 2-3 things you can apply. Choose one and apply it and get your answer. Fine. All right. So as I told, in the next session, we'll be seeing effect of dielectric on capacitance. Again, this will be very interesting. If you like this session, do press the like button, share it with your other friends who are preparing for their boards and competition, subscribe to our channel, and do not forget to click on the bell icon so that you'll never miss any update from us. We'll meet up in the next session. Till then, keep learning from